Hello everyone. In this video, let's see search in a 2D matrix question. So we are given a m cross n integer matrix with the following properties. The row the rows are sorted in non-decreasing or ascending order, and the first integer of each of the rows it's greater than the last integer of the previous row. So we can also say that the rows or the columns are also kind of sorted order in the ascending order, and the rows are also sorted in a ascending order, and will be given an element called as target, and we need to find out that if that element exists in the matrix or not. Okay, so that's basically the question. So as the target is 3, so here we get 3 exist in the matrix, so we will return it as true. We have to return as true or false, and they're expecting that we should have a solution of m cross n, log of m cross n time complexity. So let's start. So first solution that we can think of is a normal brute force kind of solution, right? So in the brute force, what we can do is will traverse through the matrix, and will traverse like normal traversal, will traverse through each of the values, and then we'll check if that equals to the target, then we can return true, otherwise we can return false. So if I try to write a pseudo code for that, so m is the number of rows and n is the number of columns. So the pseudo code for this will be for I is equal to 0 to m minus 1, and for j is equal to 0 to n minus 1. We'll go and we'll just simply check if nums of ij, if that is equal to target, then we could return true. And after doing everything, after doing all the traversal through all the values, if we are not able to find it, we'll simply return false. So this is the most basic solution that we can think of to solve this problem. So the time complexity will be like we have two loops. First one is running m times and second one is running n times. So we'll have of m cross n time complexity, and the space complexity will be of 1 because we are not using any auxiliary space. So the second solution, so this was it. So the second is a kind of a better solution. So we are given that the rows are sorted in ascending order, right? So when we have ascending or increasing order, increasing or non-decreasing order, and we have to find the target. So we can think, so both of the situations, they correspond to one algorithm that we can think of, that is binary search. So what we can do is we'll apply binary search on each of the rows, binary search on the row, on each row. Okay, as the row is sorted, and then we'll check that if we can check if the element, if that exists, then we'll simply return the index of that element, or we don't have to return the index, so we'll simply return true. And after all the traversals, if the element doesn't exist, then we'll return false. One more optimization we can do it is like first we can find out if a target it's there, if it lies within the range of the first element of the row of a row and last element of the row or not. Like one small, we can optimize our approach by using this. If the target, if first we'll check if that lies in this range, then we can do the binary search on that, right? And yeah, so if I do the dry run of this approach, first will so let me first write the pseudo code actually. So the pseudocode of this solution would be something like for I is equal to 0 to m minus 1. We'll traverse each of the rows. Okay. And first we'll check if nums of I and 0. Okay. If that is less than or equal to target, and then okay, nums of I of n minus 1, that is the last element of that particular row, if that is greater than or equal to target, Yeah. Yeah, so from this we can infer that the target lies in that range. So we will write a simple binary search that will take the nums of I as the array, and it will search for the target. And we can program the binary search to return the, okay, so let's say it returns the index. Okay, if binary search of this is not equal to -1, we can program it, the binary search, that we can simply, if we can return -1 if the element is not found, otherwise we'll return 1. If the element is not equal to if the output is not equal to -1, we'll simply return it as true, that we have found this target in the array. Otherwise we'll continue searching for rest of the rows, and once we are done with all the rows, if we don't find the element, we'll return it as false. Okay, so the binary search code, I'm assuming that that's a straightforward binary search, and you can watch some of my other videos wherein in the basics of algorithms and DSA, I have covered the binary search, so you can watch that, or any other YouTube videos or blogs also you can read. So this is a straightforward binary search. I'm not implementing this. So if I try to dry run this approach, okay, so first of all, we have the target as 3, okay, and we are considering the first row itself. So where is the cursor? Yeah, I'm a bit new to this cons. Okay, yeah, so we are on the first row. Okay, and we are at the element 1. Okay, so that's the first element of the row. First we'll check that if the target, does it lie between this range. So yes, so the target is greater than 1 and target is less than 7, so target lies in this range only. So we'll take this row and we'll apply binary search. So the mid will be calculated, like I'm also trying the binary search part, so let's try. So the mid will be 0 plus so this index will be 0 1 2 3. Okay, 0 plus 3 by 2, that is 3 by 2, and we'll take the integer value, that is 1. Okay, and then we'll check with the mid. So yes, we have indeed found 3 and the mid value is correct, and the mid value is itself the target, so we will return its index, that is 1, and as the return type, that is not -1, so we'll simply return it as true, that we have found the element, right? Found. Right. Okay, so the time complexity of this approach would be something around m, that is the number of rows, and here we are applying binary search on nums of I. Okay, nums of I has how many elements? It has n elements, that is equal to the number of columns, number of elements, right? So for the binary search, we know that it takes log of n to the base 2, as we are every time we are dividing the search space into half, so it takes this time complexity to find an element with the size of, in the array of size n, so it will have the time complexity of O of log of n to the base 2, and the space complexity will be O of 1. Okay, so this is the better approach. So how we can optimize this approach, because in the question we have also been given a hint, right, that we can develop of algorithm of log of m into n complexity. So how can we do that? Okay, so let's move on with the most kind of optimal solution. So wherein we'll try to apply the, we have to think of something of log of m to the n complexity, m into n complexity, that is O of log of m plus log of n. Okay, so here we have to optimize this m to log of m. So I am thinking something around, what if we apply the binary search to all the values in the matrix. Okay, and how can I, so for that, do I need to sort the values, or do I need to, like, store it in a temporary vector and sort the values again? No, right, because it will take like, this is one approach, but it will take a space complexity of m cross n as well, and overall we have to traverse the array, so it will take the time complexity as well of O of m cross n. So this is of not of use, not of much use. So what if we find a way to flatten the matrix to 1D sorted array, and that too in place. and then we just apply binary search on that array. Okay, so let's take an example. How can we get an index to let's say if we want 16, okay, or let's consider 20. We have the value as 20, and that is nums of 1 and 3, right? So the row is 1 and the column is 3. So how did we arrive at this one, right? So we can arrive at this. So how can we get the index, like this values correspond to the indices in the 2D matrix, right? 2D matrix. But how can we get the 1D index? Or if we have the problem, like if we have the 1D index, okay, how can we get the 2D matrix values? That's the question. So what if we so to get the row number, how about we divide that by the number of columns, index by the number of columns, and the column number we could get, this is equal to, actually this is we could get by index moduli number of columns. Okay, so how does this work? Let's take an example of 20. Okay, so nums of so if I have to, I'll just copy this array 1 3 5 7 10 11 16 20 23 34 1 3 5 7 10 11 16 20, and we have 23 30 34 60. 60. Okay, so this is our matrix, and I have taken this 20 value, so that corresponds to row number 1 and column number 3. So let me, I can first I'll represent it as a 1D sorted array. So it will be 1 3 5 7 10 11 16 20 23 30 34 60, and okay, so this will be, and this I'm taking the indices, okay, in the 1D array 1 2 3 4 5 and 6. Okay, so I have the index of 20 as 7. Okay, so the formula that I was talking about earlier, the row number will be 7 divided by the number of columns. The number of columns is 4, the number of rows is 3, number of columns, that is equal to 1, and the column number I'm doing 7 moduli 4, that is equal to 3. Yeah, so indeed we have the value 20 at row number 1 and column number 3, right? So this we can consider it as a formula also, that divided by the number of columns gives us the row, and moduli by the number of columns gives us the column. So this is valid because we have also been given a condition that the last element of the previous row, it is always smaller than the first element of the next row. So we can always arrange it as a sorted order directly while directly traversing. Okay, so this comes out to be sorted order directly. So using this formula, we can consider, like, we can apply a binary search on the entire, we will just have imaginary 1D array. Will imagine that 1D array will not actually traverse and create that as a separate vector or anything. We'll imagine that as a 1D array. So the index, okay, that will start from 0, the index, and the end of the index, okay, okay, this is not index, this is the low, actually low pointer, and the high pointer will be corresponding to the index of m into n minus 1. So this is the last index of the last array element. Okay, and we can do the normal binary search while low is less than equal to high. Okay, we'll find the mid. Okay, mid will be low plus high by 2. Okay, and if we get the mid as a target, if nums, okay, so first, before doing that, we haven't converted this into 1D vector, right? So we need to find out the row number. So row number, as we got from the earlier formula, it will be mid by n, and the column number will be mid mod n. Okay, and then we can find out everything, and we'll compare everything in terms of the original nums 2D matrix, and we'll just move the mid, low and high pointer in our imaginary 1D array. Okay, so I'm taking if nums of row call, if that becomes equal to target, then we can simply return it as true, right? Else if, okay, if that comes out as greater than target, is greater than target, so the target is quite smaller as compared to this value. Okay, so we'll have to trim down the search space, and we'll have to move to the left side more, like the smaller value. So we can do high is equal to mid minus 1, or else if the value is smaller, if the nums of row call is smaller than the targets, that means that the target is a larger value, so we can move to the right hand side, that is we can move the low pointer to the mid plus 1 location. Okay, and we'll do all the binary search, and if we don't find after the binary search as well, we could return it as false. So the time complexity of this approach, it would be so as the search space is of m cross n, like 0 to m cross n minus 1, so it's m cross n, and we are performing a binary search, so the time complexity will be log to the base 2 of m cross n, right? And the space complexity will be big of 1, because we are not storing a new vector, no new vector, no new vector, or no traversals as well. Yeah, so this is the space complexity. So let's now move to the lead code, and I've already coded the solution. I'll just walk you through. So let me walk you through the code, the optimal code only. You can code the all your solutions as well. That would also pass, because the constraints are not much. The constraints are 100 only. So even if we code log of m into n solution, that becomes a 10 raised to the power 4. So it would also pass, but we'll try most optimal solution. So here we have initialized the low and high pointers, and we'll calculate the row and column, and then if we find the target, we'll return true. Otherwise, if the matrix of row call, if it's less than target, then we'll move to the right hand side, and we'll do low is equal to mid plus 1. Otherwise, we'll do high is equal to mid minus 1, like move to the left hand side, and at the end we'll return false. So let's try to run this. So it's running, and let's try to submit this. Yeah, so it's getting accepted. Yeah, so that was it from this video. If you have any other doubts, you could ask in the comment section. I'll try to discuss, and if you have any other approaches as well, or anything I could improve upon, to share me in the comments. Thank you.